Right, so we're going to talk about free radical substitution, one of the many reaction mechanisms you need to know. And we're going to start off with a relatively simple example. And that's going to be methane. So CH4, we're going to react it with chlorine. And what we're going to produce is methyl chloride, chloromethane, either way, we'll call it chloromethane, and hydrogen chloride, HCl. So we're going to talk about that reaction. Most of the time, you're quite happy saying that this is the reaction, it's balanced, everyone's happy, the world's a good place. In organic chemistry, we need to go a bit further. We need to go say how this reaction happens. Because if I sent you off and going, you find some methane, you find some chlorine, let's put them together. One, I'd probably get sacked because methane, very combustible, not that safe, and chlorine, much more dangerous, very poisonous gas. So we're not actually going to do this reaction, but I'm certainly not going to send you off to find it remotely. But we do need to be able to talk about how this reacts. So we know that methane combusts really well. We know that chlorine's quite reactive as well. But put them together, nothing will happen. They're both relatively stable. Well, they're both very stable molecules, but when you put them together or you try and heat them up, nothing's going to happen. So we need to make this reaction happen somehow. And to do that, we do something called an initiation step. So initiation basically just means we're starting the reaction. And we're just going to totally ignore the methane. The methane can just sit by itself somewhere in a corner. We don't care about it. The chlorine, however, this is where things get fun. So that's Cl2. Chlorine gas, two chlorine atoms with a covalent bond between them. A covalent bond is just a shared pair of electrons. Covalent bonds are really, really strong. So we need to break it somehow. And the way you're going to break a chlorine-chlorine bond is by using UV light. So we're going to get some UV light to attack that chlorine-chlorine bond. And what's going to happen is your shared pair of electrons, one of the electrons from the bond is going to move to the chlorine on the right. The other electron is going to move to the chlorine on the left. I just thought I'd confuse you there by trying to say the opposite one at the same time. I do know my left and right, I promise you. So you'll notice here what I've drawn are two curly arrows with kind of like a fish hook end. So just half an end of an arrow, haven't done both ends. That's because in organic chemistry, if you draw a curly arrow, that tells you the movement of a pair of electrons. And most arrows obviously have 2 points at the end. These only have 1 point at the end, so it shows the movement of one electron. So one electron went to the chlorine on the left, one of them went to the chlorine on the right. So what we have done here, and I'm going to try and do these in different colours and then try and keep the colours consistent throughout, is we've made what is called a chlorine radical. So a radical is just something which has an unpaired electron. So when you think about it, that chlorine had 6 electrons around it and then 2 in the covalent bond. One of the electrons has gone back to the initial chlorine, so now it's got 7 electrons. Electrons always come in pairs, so if you've got an odd number, it must be unpaired. So what we've got there are chlorine radicals. Now, electrons don't like being unpaired. Electrons would quite like to pair up in some kind of bond. That's how you're going to get a stable molecule. So, chlorine, pretty stable. Chlorine radicals, unbelievably reactive. They're going to want to react with anything. And in this equation, they're going to want to react with methane. So, that takes us on to the propagation step. And you'll notice I put a 1 there. Why? Because there's more than one propagation step. So we've got a molecule of methane. And we're going to react it with one of these chlorine radicals. So we made the chlorine radical in the initiation step. We're using it in the first propagation step. You'll notice that a lot in this, we always use something we made from the previous step. So you saw in the initiation step, we used UV light to break a covalent bond. Another thing that can break a covalent bond is a radical. And we're going to break a carbon-hydrogen bond. Doesn't matter which one, but we're going to do the one on the right just because it's the closest and easiest to show what's happening. So one of the electrons in that covalent bond, a shared pair of electrons, is going to move onto that carbon. Came from the carbon originally, it's now moving back there. That's nice of it. The other one is going to go back to the hydrogen. But rather than showing it go to the hydrogen, we're going to show it going between the hydrogen and the chlorine. And then the electron on the chlorine is also going to go there. So we've got two electrons meeting in the middle of hydrogen and chlorine. They're going to form a bond. So what we've got now is the hydrogen and the chlorine bonding together. I'm going to write it like that so you know that that red chlorine is now part of the hydrochloric acid. And we're left behind with this thing. Now this is a methyl radical. So the electron's gone back to the carbon. It's got 2 electrons in that hydrogen carbon bond, 2 in that one, 2 in that one, which makes 6. And the one that's come back from the carbon-hydrogen bond. So it's now got 7 electrons altogether. That's an odd number, so we've got a methyl radical. So, like I said, radicals, really reactive. That radical is going to want to react with something, and this happens in propagation step 2. So we've got this methyl radical. Now, that methyl radical could react with this radical here, but it takes a lot of UV light to break a chlorine-chlorine bond. So these are quite unusual in your mixture. What's a lot more common is the chlorine that you started off with, and that's what we're going to react this with. So, like I said, the radical is going to attack the covalent bond and is going to break it. So one of the electrons will move back to the chlorine. And we're going to do the same as we did up here. We're going to form a bond between, or the electron's going to move between the carbon and the chlorine to make a bond. So now what we've got is that, and we've made a Cl radical. So what you'll notice about this is that in step 1 we used a chlorine radical. In step 2 we made a chlorine radical. So we're using it at the start of the first step, we're making it at the end of the last step. So that chlorine radical, if it wants, can go back into this step. That chlorine radical hasn't been used up in the reaction, but helps the reaction progress. So think back to your GCSE days. What do you call something that kind of helps a reaction go but doesn't get used up itself? The chlorine radical is a catalyst for this reaction. And as long as we've got chlorine radicals, we can keep reacting more and more methane until basically the methane's entirely used up. But the chlorine radical should never get used up itself because it keeps reproducing in these propagation steps. And that's why it's called the propagation step, because it helps the reaction keep going. So how do we end the reaction? Well, what better name than termination? So if we think about what could happen at the termination step, let's look at the pattern that's happened so far. In the initiation step, we started off with a normal molecule and made two radicals. In the propagation steps, we had a normal molecule and a radical react together to make a radical and a normal molecule. Same here, radical, normal molecule reacts to form normal molecule and a radical. So in the propagation steps, there's one of each on both sides of the equation. Initiation, start with a normal molecule, just make radicals. So the termination step, we're just going to get radicals and we're going to produce a normal molecule. So if we get the methyl radical that's produced in step 1 and react it with the chlorine radical from step 2, ignore that. That wasn't purple, wasn't it? The two electrons in the radical are going to come together to form a covalent bond. And you're going to make chloromethane. Look at that. That's what we wanted in this initial reaction. So we started off with a methane and a chlorine. We produced methyl chloride. Why do I keep calling methyl chloride? Chloromethane and HCl. Don't forget that we made HCl in this step as well. Okay. So this isn't the only termination step that can happen. There's actually two others. So the second termination step, like I said, we made a radical, chlorine radical here, chlorine radical here. What was if they come together? That's going to make Cl2, so two radicals producing a normal molecule. And the third termination step, that's going to be if two of the methyl radicals come together. Now we're going to make ethane. So there's three different termination steps, two propagation, one initiation. In the exam, they might not tell you what termination step to do. But there's one very simple thing to do at this point. Look at the reaction they're talking about. In free radical substitution, you're always going to produce a halogen alkane, or halogen-alkane. So, in an exam, if they don't tell you which termination step to use, choose the one that produces the halogen-alkane. They might talk about these two as well, but only talk about them if they specifically ask for them. If they don't, talk about the one that produces the halogen-alkane. So, in summary, this is what's going on, and you need to be able to draw those reactions. You don't need the arrows for these reactions. You will for all the other reaction mechanisms. So what goes on, you've got an initiation step where the chlorine gets broken into two Cl radicals using UV light. Then you've got the two propagation steps of methane plus a radical goes to CH3. And I'm going to put the dot on the carbon because that's basically where the extra electron is. That's where the radical actually is. And HCl, don't forget about that HCl. Then you've got the second propagation step with the methyl radical reacting with Cl2, which reproduces the methyl radical and the halogen-alkane. And then the termination steps. Two CH3s could possibly produce C2H6. Two Cl radicals are going to produce Cl2. And the one that we really care about, methyl radical plus chlorine radical, produce the halogenoalkane.